And the first thing we'll be looking at is the introduction. We'll be introducing it. We look at the laws. We look at some questions. We examine exponential functions, decimal powers and base. Then we look at how we can solve simple simultaneous and quadratic equations using indices. Then we'll finally take questions. So let's begin the introduction. Basically, indices or index notation is just a short way of writing the product of numbers. For example, you have a number 2 times 2 times 2 times 2 times 2. Instead of writing 2 times 2 times 2 times 2 in 5 places, you simply say 2 raised to power 5. Are you getting it? So this is just what we use it to do. Or you have a times a times a. Instead of writing it this way, just say a raised to power 3. Fine. So let's look at the laws. So the basic laws of indices. The laws. Laws of indices. So let's look at the basic law. The first one says that if a, you say a raised to power x times a raised to power y, then you are going to have a raised to power x plus 1. The same thing as any raised. For example, I have 3 squared times 3 raised to power 1. The same thing as saying 3 raised to power 2 plus 1, which is what? 3 raised to power 3, or 27. Are we there?
Yes.
So this is the first law. 1. The second one, if a raised to power x divides, is used to divide a raised to power y, you're going to have a raised to power x minus y. Are you getting it?
Yes.
For example, you have 3 raised to power 5 divided by 3 raised to power 2. The same thing as saying 3 raised to power 5
minus
2. Yeah. 3 raised to power
3.
3. I'll show you something. 3 raised to power 5 is like 3 times 3 times 3 times 3 times 3 over 3 raised to power 2 is what? 3 times 3. This will kiss this will cancel this. So we are left with 1, 2, 3. 3 raised to power 3. So you can see. So this very short way, you just pick the powers, subtract them, and you have the answer. It's very easy. So that's the purpose of this. The third law we'll be looking at. If you have a raised to power x, a raised to power x, all in a bracket, then you now have y outside of it. It's the same thing as saying a raised to power x times y. Are we there?
Yes.
For example, you have 2 raised to power 3. You now say everything raised to power 2. You are going to have 2 raised to power 3 times 2, which is what? 2 raised to power 5. 2 raised to power 5 is what? 32. No, 64. 64. So 2 raised to power 5 is what? 64. If you look at it very well, 2 raised to power 3 is what? 8. Am I still correct? 2 raised to power 3 is 8. Square. 8 square is what? Is it not 64?
Yes.
64. So, you're actually good too. Then the fourth law we'll be looking at. A, B raised to power y. A, B raised to power y. We are going to have A raised to power y, then times B raised to power y. Both A and B are going to take on the power separately. For example, you have 3p cubed. 3p cubed. I now say squared. 3 will take on the power separately. P is going to take on the power separately and cube. So you're going to have 9p squared q squared. That's another one. Is anybody lost?
No.
Fine. Then another one is this. A raised to power 0 is going to give you 1. Anything raised to power 0 is what? 1. For example, if you see 3 raised to power 0, we have 1. Let's look at it. If I say A raised to power 3 divided by A raised to power 3, going by the second rule is going to be what? A raised to power 3 minus 3, which is what? A raised to power 0. Are we there?
Yes.
But then, let's call this one, let's call it star. But then, A raised to power 3 divided by A raised to power 3 is like, divided by A raised to power 3 is like A times A times A over A times A times what? A. All this one will cancel one another and you have 1. So this is 1. That means this first A raised to power 3 divided by A raised to power 3 that give us A raised to power 0 here. If we handle it in another way, we are going to have what? 1 as our answer. If these two are the same, that means this is going to be equal to this. Therefore, A raised to power 0 or anything raised to power 0 for that matter is what? 1. So we'll move to the 6th law. So here, if we have 1 over A, is the same thing as saying A raised to power minus 1. Are we there?
Yes.
We just invert it. The inverse law. 7 is similar to it. So if you have A raised to power maybe n, it's going to turn to A raised to power what? Minus n. Hope you are there. For example, A raised to power 2 is the same thing as saying A raised to power minus 2. 1 over A raised to power 5, same thing as saying A raised to power minus 5. If you look at it very well, it's actually this 1 over that is bringing the negative. 1 over is bringing the negative. So this power here will take a negative sign if you remove this inverse. Are we there? So you have 1 over A raised to power 5, you have this. So generally, this holds. Generally, this one is true. We'll now move to this one. If you have the nth root of A, is going to turn to A raised to power 1 over n. I hope you are not lost. Let me break it down in what you understand. Bringing this 8th law now. For example, you have the third root of A. You are going to have A raised to power 1 over 3. The fourth root of A means A raised to power 1 over 4. The 5th root means what? A raised to power 1 over 5. So if you just write A, this, what are we saying? We assume it is what? 2. So this one is A raised to power half. So let's quickly look at the application. Some questions, there are sweet questions that we have in our question bank here. I'll just, let's look at some questions, some examples of the applications of this law. The first one will be, we have simplify. That's the first one. Then the second one, we'll be picking examples A and D. Let me pick A and D. Solution. So let's start with A. 8 raised to power 1 over 3. I hope you know that 8 is 2 raised to power 3. Are we there?
Yes.
Okay. Then raised to power 1 over what? 3. So this 3 is power, this 1 over 3 is also a power. So they will take care of each other. So 3 is going to cut 3. So you are left with only 2 as your answer. We have simplified that. Then example D. Example D. We have 16 over 81 raised to power minus 3 over 4. 16 is 2 raised to power 4. Hope you know.
Yes.
So this is 2 raised to power 4. Then 81 is 3 raised to power 4. 3 raised to power 4. Hope I'm still correct. Then you have minus 3 over 4. Are we there? So we have, I can write it this way, 2 over 3. Everything raised to power 4. Then times the minus 3 over 4 that we have here. Is anybody lost? No, fine. So this 4 can take care of this 4. So you are going to have 2 over 3 raised to power minus 3. We can simplify further. You can simplify further. So you have, this is like 1 over 2 over 3 raised to power what? 3. We have removed this negative. It just means 1 over. 1 over. So you have 2 over 3 here, raised to power 3. This is like 1 over 2 raised to power 3 is what? 8. 3 raised to power 3 is what? 27. So this is now like 1 divided by 8 over 27. So it's going to turn to what? 27 over 8. If you have 1 divided by any number, a over b, right? It's going to turn to 1 times b over a. So 1 divided by 8 over 27, 27 is going to climb up. It's now turn to 1 times 27 over 8. Hope you are not lost. So how many 8s can we have in 27? We are going to have 3. Then remainder 3 over 8. So this is our final answer. So next we'll be moving to exponential functions. But before we move to our exponential function, let me just give you a very quick question to play with. Just play with this. 16 3 over 4 times 4 raised to power half over 8 raised to power 5 over 3. Just simplify this. The answer should be half. You should get half. Then we'll now move to our exponential function. Exponential
Function.
So we see that when an unknown, or an alphabet, when an unknown, in most cases represented with alphabet, an unknown is the index or power of a function. Then we have and what's exponential? Exponential function. For example, if you have 2 raised to power x is 8. This x is the unknown. So you represent it with what? An alphabet. This kind of equations, you say they are exponential functions. For example, if you want to simplify, you can just have 2 raised to power x is what? 2 raised to power 3. Are we still there? Because they have the same base, 2 here, 2 here, they can take care of each other. So you'll be left with what? X over 3. So there are some questions we'll be looking at from our bank. The first question that we'll be trying, 2 raised to power x equals to 16. Find the value of x if a, that's 1, 2, 3 raised to power 2x equals to 27, 3, 27 raised to power x plus 2 equals to 9 raised to power 2x, and the final one we'll be looking at 9 2x and 3 raised to power x plus what? So I'll just be picking perhaps 2 and 2 and okay, let me pick 3, 4. So I'll solve 2 and 4 for you. Then you play with the remaining 2. So let's take the solution. The solution. Like I said, I'll pick 2. 2 says 3 raised to the power 2x equals 27. 3 raised to the power 2x. If I write 27 as 3 raised to the power 3, I hope I'm still right.
Yes.
Fine. So 3 will take care of 3. That means that 2x is now 3. Therefore, x is what? 3 over 2. Or x is 1.5. That's the solution to the first one. Then this second one, I'll be taking number 4. 9 raised to the power 2x minus 3 over 3 raised to the power x plus 3 equals to what? 1. If I rewrite it this way, that 9 is 3 squared, then you have these 2 over, oh, you know what I did? 9 is 3 squared. Then you have the denominator, 3 raised to the power x plus 3 equals to what? 3. No, sorry. Equals to what? 1. Are we still alright? So we'll move on. So from here, again, 3 raised to the power 2 into 2x minus 3 over 3 raised to the power x plus 3. The cell equals to what? 1. So this guy will go this way. You're going to have 3 into 2 minus 3 equals to what? 3 raised to the power x plus 3. I've transferred this one to the side by multiplying it with 1. So you have 3 taking care of 3.
Yes.
The bases are the same. So you are left with 2 into 2x minus 3 equals to what?
X plus x plus 3.
2 into 2x, you have 4x minus 6 equals x plus what? 3. So you collect like times.
Yes.
Are we there? So let's take x to the left side. We're going to have 4x minus x equals to plus 3 plus 6. It was minus here. By the time it crosses this sign, it's become what?
Plus.
Positive. So we are going to have 3x as 9. X is what? 9 over 5. X is what? 3. So we'll move to decimal powers. So decimal power and base. So let's look at some quick examples. Simplify. The first one, you have 32 raised to the power 0.2. The second one, you have 0.027 raised to the power minus 1 over 3. So the third one, 0.25 raised to the power x minus 1 equals to 32. So I'll be picking 1, then I'll be picking 3. 1 and 3. So solution. The first one, we have 32 raised to the power 0.2. Do you know that 0.2 is 1 over 5? Hope you are correct?
Yes.
Okay. That means I can rewrite it this way, 32 raised to the power 1 over 5. And I'll not be wrong. Of course, 32 is what? 2 raised to the power 5. So you have 2 raised to the power 5 raised to the power 1 over 5. Fine. So 5 is going to take care of 5. So the left with ordinary 2. Then number 3, we have 0.25 raised to power x minus 1 equals to what? 32. 0.25 is the same thing as 1 over 4. Are we there?
Yes.
It's 1/4. So I can just rewrite it and put 1 over 4 raised to power x minus 1 equals to what? 32. We said 32 is 2 raised to power 5. So let's just put it. Okay, let me rewrite 32 and take it step by step. So this one is like 1 over 2 squared. Are we here? 4 is just 2 squared. So what do? You transfer this one up. So you're going to have 2 raised to power minus 2 x minus 1 equals to 2 raised to power what? 5. I can take out this minus 2 so that we'll have 2 raised to power minus 2 is now outside. You should be multiplying x minus 1. Then you have 2 raised to power. Somebody's lost. Let me go over it once again. You have 1 over 2 raised to power 2. And I told you that one of the laws of indices, if you have a raised to power n, is anything as a raised to power what? Minus n. This 1 over means negative. So that's what we are doing here. Instead of 1 over 2, we just have 2 raised to power negative. Then this power will remain. Do you get it now?
Yes.
Fine. So you have 2 raised to power minus 2. So these 2 can take care of these 2. You'll be left with minus 2 into x minus 1 equals to what?
5.
5. So you have minus 2x. Minus 2 times minus 1 is what? Plus 2. 5. Are we getting it?
Yes.
Let's continue this side. So you are going to have minus 2x equals to 5. By the time you transfer this 2 to the other side, it's going to turn to minus 2, negative. Are we following? So you are going to have minus 2x is what? Equals to 3, such that x is 3 divided by minus 2. So that x is what? Minus 1.5. So we are through with decimal powers and base. We now look at how we can use indices to solve simultaneous and quadratic equations. So that's what we'll move into next. We'll quickly take some examples on how to use indices to solve simultaneous and quadratic. The first one, if if 7 raised to power 2x plus y equals to 1 and 5 raised to power x minus y equals to 125, find x and y. Awesome. This is sweet. So let's look at it. We have 2 equations already. Yes. That shows a simultaneous equation. We are going to solve this. We're going to solve this. So let's try and simplify the solution. The first equation says that 7 raised to power 2x plus y equals to 1. 7 raised to power 2x plus y. I said anything raised to power 0 is what? 1. If I say 1 is 7 raised to power 0, am I correct? Anything raised to power 0 is 1.
Yeah.
That means I'm correct. So instead of writing 1, I can put 7 raised to power 0. Why am I doing that? So that this guy can take care of this guy. Are we there? That means you now have 2x plus y equals to 0. Call that one equation 1. Then you pick this one. The second one. 5 raised to power x minus y equals to what? 125. That means 5 raised to power x minus y equals to what? 5 raised to 125 is 5 raised to power 3. So this guy will take care of this guy. You are going to be left with x minus y equals 3.
Equation
Equation 2. So we now solve equation 1 and 2 simultaneously, using simultaneous equation. Solving 1 and 2 simultaneously. Simultaneously means at the same time. You're going to have it this way. Let's add 1 and 2 together. Add equation 1 and 2. Add equation 1 and what? Equation 2. If you add equation 1 and 2, that means you are adding 2x plus 2x. You are adding minus y plus y. Are we there?
Yes.
You are adding 0 plus 3. We'll get to something else. We'll expand on that. So 2x plus x. You are going to have 2x plus x plus y minus y. Y minus y equals to, are we there? 0 plus 3. 0 plus 3. So this one will take care of this one. Y minus y is 0. You're going to have 0, 0 here. So you'll be left with 2x plus x is what? 3x. So 3x is 0 plus 3 is what? 3. So x is what? 1. That's the first one. Then let's try to get y. Using this second equation, you can use either of them, but let's pick the simple one. Using equation 2. From equation 2, we know that x minus y is what? 3.
3.
So you now substitute x equals to 1 in the second equation. In equation what? In equation 2. So you're going to have, instead of x minus y equals to 3, you now have 1 minus y equals to 3, such that minus y equals 3 minus what?
1.
Fine. So that minus y is what? 2. So you take this y to the other side. So that y will now be what? Minus 2. Therefore, our x is 1 and our y is minus 2. Our final answer. So we'll now take another question that will solve a quadratic equation. This one is simultaneous. Then we'll go into quadratic. Examine a simple question in quadratic equation that we're using this is to solve. Example, let's look at this question. 5 raised to power 2x plus 1. 10, 5 raised to power x plus 5 equals to 0. So this question is an exponential function that we're going to simplify, and it is turned into a quadratic equation that will solve. We are told to find x. Solve for x. Solve for x. This one is 5 raised to power 2x. But take note, if you have a raised to power x times a raised to power y, you're going to have a raised to power x plus y. A raised to power x plus y, as you already learned in our equation. That means if you have a raised to power x plus y, something like this. If you go back, you have a raised to power x separate plus a raised to power y separate. Are we there? A raised to power x separate, a raised to power y separate. That means if you have something like this, you can see 5 raised to power 2x separate, then 5 raised to power 1 separate. 5 raised to power 2x separate, 5 raised to power 1 separate. Is multiplication, sign multiplication. So instead of this, you can now say 5 raised to power 2x separate times 5 raised to power 1 separate. Are we there? Then you move on. 10, it this way, I am still correct. It's still the same 2 times x, or x times 2 is the same thing. Times 5 minus 10 raised to the power 5x plus 5 equals to what? 0. Now, this is the only sense of what I've been trying to do. I have 5x here, 5 raised to the power x here. So, I've been looking for a way to bring out 5 raised to the power x from this equation 2. And that's what we have achieved here. Are you getting it? So, let that 5 raised to the power x, you say let it be maybe p, so that you're able to solve. So instead of putting 5 raised to the power x, you put p. Wherever you see 5 raised to the power x. So this one you're going to have p squared. Instead of 5 raised to the power x squared, you have p squared. Times what? 5. That's 5p squared. Minus 10. Then p. Instead of 5 raised to the power x, you put what? P. Plus 5 equals to what? 0. This one is like 5p squared. 5p squared minus 10p. This equation is a quadratic equation. We cannot solve it. We cannot solve it. This is a quadratic equation. We cannot solve. So you solve 5p squared minus 5p. Don't worry. By the time we get into the other parts, we'll be able to do it very well. Equals to 0. 5 into p minus 1 minus 5 minus 1 equals to 0. 5p minus 5 bracket p minus 1 equals to 0. So if a times b is 0, it is either a is 0 or what? B is 0. Sure? If you multiply A and B and you get 0, either A is the one that is 0 or B is the one that is 0. So because of that, if this and this are multiplying and you have a 0, it is either 5p minus 5 is 0 or p minus 1 is the one that is 0. Is anybody lost?
No.
Fine. So you have 5p equals to what? 5. You have p will be equal to 5 over 5. And that's what? 5 divided by 5. So p is 1. Or, let's deal with this. Also, this one is too sweet. So, minus 1, you transfer it to that side. So in both cases, p is the same. P is 1. But we are not looking for p. The question says, solve for x, not solve for p. So that means you are not yet true. We are not yet true. So, you now put back, substitute. You now substitute back, substitute 5 raised to the power x. Or just go back, 5 raised to the power x, we said is p. So, equals to 1. We are looking for x, not p. So when you get to p, you still continue. So what do we have? You can say 5 raised to the power. Of course, anything raised to the power 0 is 1. So instead of putting 1 there, I'll put 5 raised to the power 0. Fine. This guy is going to take care of this guy. And that means what? Our x is what? 0 as our final answer. So I'll just give you some questions to play with on your own. And that will be the end of everything in this index notation. And that's all. Welcome to this segment on logarithm. The logarithm we'll be looking at is the one that's related to indices. The use of your normal four-figure table. We'll be treating that under trigonometry. So you watch out for that segment. So quickly we'll be looking at the relationship between this and logarithm, the applications of this relation, the laws of logarithm, application of the laws, substitution and so on. So let's start with the relation between indices and logarithm. logarithm. We said if you write the logarithm of a number y to the base b, if you say it is x, you are saying the logarithm, which is x, is actually the number which this b will be raised. The number which b will be raised to give us what? y. This one is what you call the logarithm form, or just a log form. And this one is the indices or index form. Index form. So this is the relationship between indices and logarithm. If you have log y to base b, b raised to power x will give you y. Note, b, a slave here, is remaining a slave even though you have removed the log. So let's quickly look at the applications of these laws by checking some examples very quickly in our bank. For example, log 10, log 100 to base 10. If it is x, find x. By this relation, if we say b raised to power x, it should give us y. In other words, if I say 10 raised to power x, it should give me 100. In other words, 10 raised to power x should give me what? 100. That means 10 raised to power x is what? 10 raised to power 2. Are we not back to our indices? We are actually back to indices. So logarithm and indices are actually interwoven. 10 will take care of 10, therefore x is what? 2. So these are stuff you can actually play with, but I'll be picking, let me pick only number 2 to solve solution. We have here that log 10 to base 0.01 equals to what? Y. Looking at the relation, we change it to the index form. The index form is, we have 0.01, a slave, it remains a slave, raised to power y, carrying y on its head, equals to what? 10. But of course, you know that 0.01 is something we can change. We can turn it to 1 over what? 100. Y. Don't be lost. 0.01. You drop a 1 here, you have 0, 0. You already have 1 over 100. So, equals to what? 10. This is like 1 over 10 squared raised to power y equals to what? 10. 100 is 10 squared. So this is 10 raised to power minus 2 equals to what? 10. I can't see. 10 raised to power minus 2y equals to 10 raised to power 1. Are we there?
Yes.
So 10 is going to take care of 10. We have minus 2y equals to what? 1, such that y is what? Minus 1 over 2. So this is the final answer. So we'll now be moving to the laws of logarithm. So quickly look at the laws of logarithm. The first one says that if you are multiplying the log of the multiplication of two numbers to any base, you can actually separate those numbers. For example, you can have log 10, perhaps you have 15, but you know that 15 is like 3 times 5. Are we there? So the law is saying that you can separate 3 and 5 so that you have log 10, log 3 base 10 plus log 5 base 10 separate. So that's the first law. Then for the second law, it says that if you have x dividing y, it's going to be the log of x minus the log of y. Are we there? For example, you can have log 45 over 10 to the base of 10 If you want to rewrite this, you can write it in this form. Log 45 to base 10 minus log 10 to base 10. That's the second law. For the third law, what we call the power law, it says that if you have the logarithm of a number to a particular power, to simplify it, you simply throw the power to the back. In other words, this n is coming to the back. For example, we might have something like log 9 to the base of 10. Of course, you know that log 9 is actually 3 squared. How do you know 3 squared is 9? So you throw this 2 to the back if you want to simplify. So you have 2 log 3 base 10. Then the fourth law, very similar to it also. But in this case, if the base is the one that has the power, so instead of having the power as a whole number that we have in the third law, it's going to be reciprocal, 1 over. Are you getting it? For example, someone might write the base 10 square, base 10 square, then you have perhaps 3. It's going to turn to 1 over 2, not 2 again, 1 over 2, times log 3 to base what? 10. So that's the fourth law. And the fifth law says that the logarithm of any number to the same base is what? 1. So that means the logarithm of 10 to base 10 is what? 1. The logarithm of 5 to base 5 is what? 1. The logarithm of n to base n is the same thing as 1. So the sixth one, the logarithm of 1 is always what? 0. That's the sixth law. Logarithm of 1 is always 0. From the relation we considered earlier between indices and logarithm, you see that this one is like a, this one is a slave here. It will carry 0 on its head. This one is like a raised to power 0, which should give us this 1. So you see that this one is true in indices. Then a logarithm is just like a little bit the opposite, but it's similar to it. The logarithm of 1 to any base is what? 0. For example, the logarithm of 1 to base 5 is what? 0. Logarithm of 1 to base n is what? 0. Then we'll now go to the seventh one. It's called the reciprocal law. In other words, it's possible for you to invert a logarithm. If you have log of 10 to base 5, if you want to invert it, you are going to have 1 over log of 5 to base 10. These two will now interchange position. If they interchange position, you now have reciprocal. Once the logarithm is now the base, and the base is now the log that you're looking for, then you have reciprocal. That's the reciprocal law. Then the last one, change of base. It says that the logarithm, if you are looking, you want to put a particular new base. If you look at this left side, there was no n as base. The base was a. So if you now introduce a new base, n, for it to be true, this is the relation. In other words, if you have log x, if the base is a, if you're introducing a new base n, you are going to have the x remains, is very potent. You put the new base divided by the former base will now be a log in itself a. Then you now put the same new base. So this one is very true. So quickly we'll be looking at some of the applications of this law. We'll look at the application of this law by solving some very, very short examples. The questions I'll give you now from our bank. So from these questions I'll pick D, E, and perhaps 2A. So solution. Let me just pick D. Number 1D. We have log 8 base 2 plus log 4 base 2. If you look at 8, you can simplify it further. 8 is actually 2 raised to power 3. Then 4 is what? 2 raised to the power 2. So this power is going to come here. So we have 3 log 2 base 2 plus 2 log 2 base 2. The same base with the log. So our loss is that one is going to turn to 1. It's like 3 times 1. Plus the same thing happens here. The logarithm of any base of any number to the same base is what? 1. So you're going to have to times 1. So this is 3 plus 2. And your answer is what? 5. So E. Let me pick E. 1E. We have log 22 to base 4 minus log 11 also to base 4. Can we combine it? Yes, let's combine it. So that we have, this one is log 2. Log 2 is going to turn to 22 divided by 11. So 22 divided by 11, we are going to have 2. Log 2 base 4. It's not easy to solve, but there's another law that we can change, the reciprocal law, that we can actually interchange the logarithm and its base. And you now have a reciprocal. The law says that if you have the logarithm of a to base perhaps n, if you want to interchange it, it's going to turn to 1 over the logarithm of n to base a. So let's interchange it so that 4 will be a and 2 will now be the base. So it's the same thing as saying 1 over the logarithm of 4 towards base 2. We can deal with this very easily. So this is like 1 over the logarithm of 2 squared. You have a 2 here. This 2 is going to come here. So you have 1 over 2 log 2 base 2. Hope you know that this one is already 1.
Yes.
Fine. So you're going to have, okay, let's move down here. You're going to have 1 over 2 times 1. So the final answer is what? Half. Half. I'll also be taking question 2a. Question 2a. So you have 2 log 5 plus log 36 minus log 9. Take note that when no base is written in the log, it's already in base 10. When you don't see any base, we assume it is 10. That's the law. So here, this is interesting. Let's throw this 2 to this side so that we can simplify. It will not look like the other ones. If you look at the other ones, there is no digits before the log. So let's throw it to the other side so that we will now have log 5 squared plus log 36 minus log 9. This one is 5 squared is 25, share? So you have log 25 plus log 36 minus log 9. So we have log. Plus means times. We want to combine the 3 together. Wherever you see plus, it means multiplication. And minus means division. So this is like 25 times 36 divided by what? 9. So 9 here you have a 1. 9 here you have a what? 4. So 25 times 4 is 100. So this is like log 10. I told you, there's no log attached. It's already 10. So this one is 10 squared. So the 2 will come to this side. So 2 log 10 is 10. This is like 1. 2 times 1. And the final answer is what? 2. So let's quickly move to substitution in logarithm. Substitution in logarithm, it involves breaking down a function into the simplest form. before you now substitute the actual value. For example, if log 3 to base 10 is 0.4771 and log 2 to base 10 is 0.3010, we might be told to find log 12 to base 10. This is how you do it, solution. If you look at 12, we can break it down to 4 times 3. Are we there?
Yes.
This one is like, if you separate it, log 4 separate, then log 3 separate. By the time you change this one, it's going to turn to 2 squared. 2 squared plus log 3 base 10. So you have 2 log 2 base 10 plus log 3 base 10. You now substitute the actual value that you are giving. Here we are giving that log 3 base 10 is 0.4771. Then that of 2 is this. So you substitute. So you are going to have 2 times 0.3010, 0.3010 plus that of 3 is what? 4771. 0.4771. So this is what you do. 2 times this, you have 0, 2, 0. 2 times 3 is 6.0. Then plus 0.471. You have 1 in plus 1, you have 1. You have 9. You have 7. You have 0. You have 1. So these are final answers. So I'll give you more questions that you can play with. Let me give you questions that you can play with. Further questions? So giving. So the final stage involves equations in logarithm. How we can solve equations in logarithm, equations that can be linear, can be quadratic, can be simultaneous, it can be anyhow. So we'll pick a very fast one, an example. For example, assuming you have log x to base 10 plus log 2 to base 10 to give us 1. We are told to find x. Quickly we do this. The solution. If you have the logarithm of x to base 10 plus the logarithm of 2 to base 10, we can say the same thing as saying the logarithm of 10 to base 10. Hope you still remember that 1. Anything raised to power. If you have the same log and the base is the 1. So you have, if you have 1. So we can put 10 there. Then if we use our law, you have this, you join 2 and 10, so you can have 2 times x to give us log 10 what is 10. We're actually changing this so that log 10 can take care of log 10. That means that our 2x is now equal to what? 10. And our x equals to what? 10 divided by 2. Which is what? 5. So, the last part, I'll be giving you questions and I'll put in the answers there so that you can solve on your own and see how far you have learned. So we have come to the end of this particular series. You watch out for other series that will be coming. So we thank you for staying with us. Bye for now.